Okay. What type of functional group is this?
Alcohol.
All right, so yeah, alcohol. So this would be a good problem for that. All right, so anyone make a suggestion? So here's our reagents. These are our reagents. Anyone make a suggestion what's going to happen first here?
I'll leave. I know, like, yeah, I will leave. I have no idea what we're...
Okay, so the first suggestion is that the I would leave. Now, that would give us these intermediates.
Uh-huh. Yeah.
Now, this should make you feel very nauseous. What's so queasy making about this? Well, here we have a charge. Nature doesn't like charges. Sometimes nature can stand charges. Is this primary, secondary, or tertiary? Primary. Is that good?
No.
In fact, it's not even bad, it's impossible. You should never make a primary carbocation this semester. This semester, you're never going to make a primary carbocation.
Why?
Well, nature doesn't like charges. The only way you can make a carbocation is if there's something to stabilize it.
Yeah, but then they have the OH to stabilize it.
All the way over here?
No. The other.
Oh, this one over here?
Yeah.
Well, that might come in eventually, but you guys wanted this to leave first. Oh, so maybe we're thinking the OH would come in at the same time. Okay, maybe I didn't understand you. I thought you guys were saying the I would leave first. Okay, my mistake. All right, so we can't form the carbocation, but you were suggesting that there would be a SN2 reaction here. Okay, now that's much more reasonable. However, that's still not what's going to happen. So let's start with this. So the basic principle, so we have to talk about acids and bases. Acid-base chemistry is key here. Anytime you have a strong acid as a reagent, what will be the very first thing that happens?
They would deprotonate a weak base.
Do acids protonate things or deprotonate? Protonates. If you have a strong acid, the very first thing that will happen is that the acid will protonate somebody.
Yeah.
If you have a strong acid, the very first thing that will happen is that the acid will protonate somebody, without exception. If you see a strong acid in the reagents, you must start by protonating somebody. No question. If we see a strong acid in the reagents, we must start by protonating somebody. Can you guys list what are some strong acids?
HBr, HI.
Hydrofluoric actually is not a strong acid. It's not terribly weak, but it's not in this category of strong acids. So you probably won't see that being used.
Oh, COOH?
That's a weak acid.
Oh.
Yeah, that's a carboxylic acid. So
H2SO4.
here's the strong acids that I think you might be seeing right now. You might not actually see nitric acid, but I put it here for good purpose. All right, you might see hydrochloric, hydrobromic, hydroiodic, and sulfuric acid. Those are the strong acids you're likely to see used right now, maybe not so much nitric acid. So if you see a strong acid, you should look for somebody to protonate. Okay. Who do you want to protonate? You want to protonate somebody with a lone pair, some electronegative atom with a lone pair, usually an oxygen or a nitrogen. Okay, so that's actually pretty easy. If you see these strong acids, you got to protonate someone first before you do anything else. However, so here we have a strong base. Here we have a strong base. Now the problem here is this a strong base? Yeah, if you look at your handout, we know that O- is a strong base in the handout. But is this a good nucleophile?
No.
Yes.
Oh yeah, it's very strong. It's a very good nucleophile.
If you look at the handout again, you can see that O- is also one of the good nucleophiles, good enough for SN2. Well, this is annoying because this could then be either a base or a nucleophile. This could be either a base or a nucleophile. So it's a little bit hard to tell which one's going to happen. However, acid-base reactions are fast. Acid-base reactions are fast. So when in doubt, you should assume that the acid-base reaction happens first. In fact, I think this semester, if there's someone to deprotonate, you should always do that instead of nucleophile. So there might be some exceptions to this, but I think this semester, if you see a strong base, you should do, your top priority, plan A, should be to deprotonate somebody. You shouldn't use this as a nucleophile unless there's nobody good to deprotonate. Okay. Well, I guess that's not 100% true, but we already saw this because we know this we could do either an SN2 or an E2, for example. Either an SN2 or an E2. And how do we decide which one it is? Well, remember, it depends how much steric hindrance there is in the substrate. So, for example, if you had, say, a methyl substrate, or a primary, well, you probably get an SN2 out of this. But if you had a tertiary, this would give you an E2.
Or even a primary or a secondary.
A primary would probably still give you SN2 because this is a very non-bulky base over here.
Oh,
this is a very non-bulky
But
base.
only primary unhindered.
Yeah, probably right. That's probably right. Good. All right. Yeah, you've really been looking at that. Okay, good. That's probably right. All right. So we know that we kind of have to look at how much steric hindrance there is to see whether this would be a nucleophile or a base. So to see whether this do SN2 or E2. However, what this really wants to do, what this would really love to do, is deprotonate an electronegative atom. So if there's a chance for a strong base to deprotonate an electronegative atom, that's going to be your top priority. If you see a strong base, you should look for an electronegative atom for that to deprotonate.
No.
Well, that would only happen if you saw this. You wouldn't usually see an acid and a base in the same reaction.
Okay.
So it would have to deprotonate.
Basically, oxygens and nitrogens, usually. You look for an oxygen or a nitrogen for this to deprotonate, usually, for a strong base to deprotonate. Okay, so again, you got to watch out. Things that are good nucleophiles are usually good bases as well, and very often the base reaction is going to happen first. Especially, again, if there's an oxygen or a nitrogen around to deprotonate, or another electronegative atom, that's usually going to happen first. So this will oftentimes act like a base instead of like a nucleophile. When in doubt, you should probably guess this will act like a base and not a nucleophile. Okay, so the upshot of that is, theoretically, this could act like a nucleophile and attack here. But is there anybody it could deprotonate, acting like a base? Yeah, this is the exact type of thing, remember, an oxygen or a nitrogen that tends to be deprotonated, all right, and which is probably going to happen faster, the acid-base reaction. Okay, so this reaction here would be reasonable if there was no hydroxy on the left. This is what would happen if there were no hydroxy, but with this hydroxy, this is not going to have time to happen. Instead, we're going to deprotonate this guy over here. Now, it's important to be able to draw the mechanism for a deprotonation, so let's make sure we can draw that mechanism.
So most of the time when they say create the products, we don't actually need to draw the mechanism out unless they want us to, right?
You don't need to draw the mechanism to get full credit, but you should draw the mechanism anyway.
Yeah.
That's right. Yeah. Pencil would be best if you got one.
Yeah.
Okay. All right, looks like some of you might need a little help with that. So, now the easiest thing is to start with the charge. Should this be at a head or a tail?
Tail.
So who are we going to put at the head?
Hydrogen.
Okay, because the whole point of this is a base that wants to pick up a proton. I'm going to go ahead and draw in the lone pair that's being donated by this arrow. Okay, now we know a hydrogen can only be attached to one thing at a time. So if the hydrogen is going to form a new bond. Right. Now I think I might have seen some of you putting the arrow pointing to the hydrogen, but that's not going to work over here. These electrons are going to go onto this oxygen over here. Okay, and then we're ready to draw our products. Well, this arrow means that this oxygen is taking its lone pair and forming a bond with the hydrogen. So now the pair that used to be on the oxygen is in this bond between the hydrogen and the oxygen. And remember that every step we're going to change the charges at the initial tail and the final head. 2 charges. Well, this is at the initial tail, so the negative becomes neutral. And then what's happening here? Well, this oxygen is gaining this lone pair. So the pair of electrons that used to be in the bond are now going to be a new pair over here, and this is at the final head. Since it started neutral, like someone said, this should be negative. How do you know what to do with the ionic bonds? Well, since this guy is losing its charge, it's going to lose the ionic bond to the sodium. And since this guy is gaining a charge, it's going to gain an ionic bond to the sodium. So the conventional way to draw this is as if there's a new ionic bond between the sodium and the oxygen. So in general, when an atom is losing a charge, it's going to lose its ionic bond, because ionic bonds are based on charges. And then the new ionic bond should be drawn between the new atoms with charges. That's the conventional way to draw this. Even though in solution these would be mainly separate ions, but it's usually drawn as if they were ionically bonded. Okay, so that gives us our products over here. Make sure that each of you drew on your paper exactly what I have on the board. TAs can be very picky about getting the arrows
We
right.
need to have that lone pair there.
Oh, except for the lone pairs, that's right. Usually people don't draw pairs. I actually think that would be a good habit though, because it shows you what's actually happening to the electrons, but usually people don't draw the lone pairs. Okay, so that gives us this. Let me just point out the most common mistake here. The most common mistake is to reverse this arrow and draw the arrow from the hydrogen to the oxygen. It's a very common mistake to draw it like this. Why do people draw it like this? Because they think the arrow shows which way the atom is going. They think the hydrogen is going here, but remember, this is wrong. The arrow is not supposed to show where the atom is going, but where the electrons are going. That's why it's good to actually draw this pair of electrons in that's moving, even though it's not technically necessary. So that's a very common mistake that people make on deprotonations, showing the movement of the proton. We're not supposed to show the movement of the proton, we show the movement of the electrons. Okay.